Hello and welcome to Mystery Science. Today we're going to be looking at Newton's second law. Sir Isaac Newton, that amazing mathematician and physicist. This slots in as CP2d on the Edexcel course, but this is universal and can be used for any exam board. What I would like you to do is just answer these questions. They're based on the mass and weight section that we have already done. So pause the video, have a go at those, and we'll be right back. Welcome back. So Brian, the astronaut, has got a mass of 85 kilograms. What is his weight on Earth? And we have to remember that gravity is 10 newtons per kilogram. So what is his weight? Well, we have to use the equation weight equals mass times gravity. And later on, I'm going to prove to you that that's actually Newton's second law. So weight equals mass times gravity. Gravity on Earth is 10 newtons per kilogram, and his mass is 85 kilograms. So his weight on the Earth is simply 850 newtons. Okay. What is Brian's mass on the Moon? Gravity on the Moon is 1.6 newtons per kilogram. Haha, I've laid you a little trap there, giving you a little bit of a red herring, because I've told you about the gravity on the Moon, which is completely irrelevant to Brian's mass. Brian's mass is 85 kilograms. It's 85 kilograms on Earth. It'll still be 85 kilograms on the Moon, unless he loses a limb on the way, or, I don't know, eats a dinosaur. He is going to stay 85 kilograms. That's his mass. There are 85 kilograms worth of Brian particles that make up Brian the astronaut. However, his weight on the Moon, now that's 85 multiplied by 1.6, which gives you a weight of 136 newtons. That's certainly much lower than his weight on Earth of 850 newtons. That's why Brian is able to leap around on the Moon. Okay, now back to Sir Isaac Newton, the amazing mathematician and physicist. Now, most of our tales of Sir Isaac Newton aren't actually true. At least we don't know that they are. I think they're inspired by actual events. For example, the famous apple that fell on his head and he suddenly went, "Ha ha, gravity." That didn't actually happen. But I think what was happening was he was actually formulating that theory, and he was thinking along these lines, and the apple falling from the tree in front of him certainly inspired him. But it makes a much better story if it landed on his head and he immediately came up with some sort of inspiration, like the apple had knocked the idea into his head. And the same thing goes along for the second law. So I don't know how much of what I'm about to say is true, but the physics behind what I'm about to tell you certainly is real. So the story goes that Sir Isaac Newton was on his way to a science fair, I think it is, at the Royal Court. And on the way, he found a rock barring the path, and he couldn't get his horse and carriage past this rock. So he got out of his carriage and he tried to push the rock out of the way, and it didn't budge. Now, you know from Newton's first law that if the rock didn't budge, there was zero motion, there was no change in motion, therefore there was no resultant force. The force that Sir Isaac Newton was applying was nowhere near the force needed to move the rock. All of the forces were still balanced, and Sir Isaac Newton's piffly little force was doing nothing. So he got his horse, and his horse was then able to push the rock aside. And Isaac Newton just kind of looked at this situation and thought, well, the horse could move the rock. The horse is much bigger than I am, so maybe, just maybe, size is important when it comes to moving things. And that's what is actually real. So if you are trying to move a large object, the larger you are, the more force you can apply. So force depends on mass. Now, if you have a resultant force, if you're able to apply resultant force, then you are going to change motion. And as we know from our work on Newton's first law and circular motion, any change in motion is an acceleration. Therefore, force is directly linked to the mass of objects and the acceleration applied to it. So if you have a resultant force moving an object, changing its motion, then that force is actually directly proportional to its mass and the acceleration of the object. Now, what does directly proportional mean? Directly proportional means that if you plot a graph of force against acceleration, you would have a nice, neat straight line, and the gradient of that straight line would be the mass of the object. Yeah? So those of you who are kind of level 8, level 9 GCSE students are now kind of thinking, well, if it's proportional and you've got the gradient of the mass and it's force against acceleration, you're now starting to think about what the equation is. It may help if I tell you the intercept for that would be 0. All right, here is a task for you. So let's break down Newton's second law. Let's write it down somewhere. And I've made it slightly easier for you. I've given you a sentence for you to write down, but sneaky me, I've changed some of the words and jumbled them all up like a sneaky imp. So what I'd like you to do, write that out and change the order of those letters to make it make sense. Pause the video and come back when you're done. Brilliant, well done. I'm sure that you've managed to get that now to say that the acceleration of an object in the direction of the resultant force depends on the size of the force and the mass of the object. There we go. And you hopefully should now have kind of thought about what the formula for Newton's second law actually is. All right, ta-da! Here is the equation. It's very simple. If you have force plotted against acceleration and you have a straight line, if it's a proportional graph, that means that we have the force is actually equal to the mass times the acceleration. Newton's second law boiled down into one simple mathematical equation. So the force is proportional to the mass and also the acceleration. So to get the force needed to move something, change its motion, you need to find its mass and then multiply that by the acceleration required, and that will tell you how much force you need to change that motion. So here is an example question. A Peugeot 206 has a mass of 910 kilograms. This is real. I looked it up. What force is needed to give an acceleration of 3 meters per second squared? Right, let's do some SRAO. You'd have come across SRAO before. If you haven't, you need to look at some of my older videos. But the equation, force is equal to mass times acceleration. S substitutes, we put in our numbers. Force is 910, that's the mass, multiplied by 3, that's the acceleration. Do I need to rearrange? No, I don't. I have the unknown as the subject. So now I work out the answer. 910 times 3 is 2,730. At the units, that's 2,730 newtons. Example 2. Now this is a Bugatti Chiron and it has a mass of 2,000 kilograms, which is close enough. What force is needed to give an acceleration of 9 meters per second squared? So again, we do exactly the same thing. E, our equation, force is mass times acceleration. Substitute in the numbers. The mass is 2,000, the acceleration is 9. Do I need to rearrange that? No, I don't. The answer is 2,000 multiplied by 9, which is 18,000. 18,000 newtons. So the Bugatti Chiron, because of its extra mass, needs a massive amount of power to move it. All right, so here are some more examples for you. I would like you to calculate the force applied to each of these objects to make them accelerate. Pay special attention to the units and the language. Some of these are a little bit different. So pause the video, have a go at those, and we'll see how you've done. Welcome back. So hopefully you've got these answers. An object of mass 50 kilograms accelerates 1 meters per second squared. 50 kilograms multiplied by 1 gives you 50 newtons. An object of mass 1000 grams. So there you go, there's the crucial unit change there. 1000 grams is equal to 1 kilogram. So 1 kilogram accelerating 2 meters per second is 2 newtons. An object of mass 70 kilograms accelerates 5 meters per second. That's 350 newtons. An object of mass 35 kilograms accelerating 10 meters per second is also 350 newtons. So there you go. There's an example of proportionality. If an object of mass 70 kilograms requires 350 newtons to accelerate 5 meters per second, if it's half the weight and the same force is applied, then it can accelerate twice as much. Now, an object of weight 800 newtons accelerates 2 meters per second. So here again, we have a unit change. We have a weight this time. So what it hasn't said is where this weight is. That's a little bit naughty. So let's assume it's on the Earth. So we divide 800 by 10 to get its mass. So we end up with 80 kilograms multiplied by 2 meters per second squared, which gives us 160 newtons. If you got all those right, well done. If you got any of those wrong, try again and see if you can get the correct answer. Okay, so here's another example question. This bike, which I am concealing the front wheel of, accelerates at 3 meters per second squared. That's after a force of 50 newtons is applied. What is the mass of the bike? So let's have a look at the SRAM. First, the equation, force is equal to mass times acceleration. Substitute the numbers in. What do we know? The force is 50 newtons. We don't know what the mass is, and the acceleration is 3 meters per second. Do I need to rearrange this? Yes, because I don't have the unknown as a subject of the equation. So what I need to do to get m on its own is divide both sides by 3. If I divide both sides by 3, I end up with m equal to 50 divided by 3. Okay, so I work out the answer. 50 divided by 3 is 16.7, and that's 16.7 kilogram. Okay, here's another example. This time the bike is accelerating 3.5 meters per second squared after we've applied a force of 100 newtons. What is the mass of the bike now? Again, let's do SRAL. Force equals mass times acceleration. Substitute in the numbers. 100 equals m times 3.5. Need to rearrange. Need to divide both sides by 3.5. So there we go. Mass is equal to 100 divided by 3.5. The mass is 28.6. It's a much heavier bike. 28.6 kilograms. All right, same again then. Here are 4 questions this time. Jot them down on a piece of paper and answer those questions, and I'll see you when you're done. Okay, welcome back. So the mass of an object that a force of 30 newtons accelerates on 1 meter per second squared. We rearrange the force equals mass times acceleration equation to get the mass. So we know that's force divided by acceleration. 30 divided by 1 is just 30, so it's 30 kilograms. Number 2, now we're calculating the acceleration. And again, here we're doing the very similar thing. We're just dividing the force by the mass, this time to get the acceleration. So the acceleration of an object of mass 10 kilograms when a resultant force of 100 newtons is applied. 100 divided by 10 gives you 10 meters per second squared. Remember the units, it's an acceleration. the mass of an object at a force of 500 newtons accelerates 0.5 meters per second squared. We're now dividing 500 by 0.5, so we end up with 1,000 kilograms. And then finally, the acceleration of an object of mass 110 kilograms when a resultant force of 300 newtons is applied. So that's 300 newtons divided by 110 kilograms, which gives you 2.72727272 recurring, which we round up to 2.73 meters per second squared. I want you to decide where you are. If you just found the last ones simple, then have a go at the gold ones. If you think you can calculate the force, but from some harder questions, have a go at the red ones. Otherwise, if you think you can do some very simple equations for the force, have a go at the blue ones. So if you can rearrange, go for the gold ones. And if you're on a higher paper, I definitely recommend you have a go at the gold ones. There's nothing stopping you from trying all three. The gold ones need some rearranging. The red ones are slightly more complicated, just force equations, and then the blue ones should be relatively simple force equations. So pause the video, have a go at those, and when you come back, I shall share the answers with you. All right, so here are the answers. If you have struggled to get these answers, then wind the video back a little bit or have a look at your working out and see if you can get to these answers. That's actually how we work very well in A-level physics. We give all of the students the questions and then they work their way to an answer. They then check it themselves against their own answer sheet, and then if they haven't got the correct answer, they work backwards and see where they've made the mistake. And this helps a great deal with learning, and then eventually, as you keep going, you won't make as many mistakes and you get higher scores on exams. Okay, so here is an example of a higher tier exam question that can be particularly nasty for the student when they look at it, because it looks as though there's information that isn't available to them, and so students tend to panic. So we're going to go through this nice and slowly. This is worth 4 marks. I was going to say it tells you that, but I'm actually in the way of that. But this is worth 4 marks, and it's worth looking at the little brackets that tell you how many marks there are, and because it kind of tells you how much information or how many steps you need. So I'm going to break down the answer in a minute. But what I want you to do first, obviously pause the video, have a go at this, see if you can get it. All right, welcome back. The first thing we need to realize is that the boat was accelerating. Therefore, there is a resultant force. And we know the force equation. Newton's second law says force is mass times acceleration. We know the mass and we know the acceleration. So that's 60 multiplied by 0.4 meters per second squared. So that gives you a resultant force of 24 newtons. That is the force, the overall force that is accelerating the boat. Now, we know from Newton's first law, and from even before that from CP1, from resolving forces, that if you have a resultant force, that comes from an unbalanced force that you can make up by adding the forces in one direction and taking away the forces in the other direction. And we're trying to work out the drag force, but we know the force of the wind on the sails. Note that it's very much bigger than 24 newtons. So we use this equation. The resultant force is equal to the force from the wind minus the force from the drag. Okay? That just goes back to resolving forces that we've done before. We're just adding bits all together. So if you take the force from the wind in this direction and then you take away the force from the drag in that direction, you'll end up with the resultant force. We know the force from the wind, we know the resultant force, so we need to calculate the force from the drag. So we can rearrange the equation. If you want to substitute the numbers in first, and then rearrange the equation, again, that's fine. So once you rearrange this equation, you'll realize that the force from the drag is equal to the force from the wind minus the resultant force. Okay, so it's really quite easy when you start to think about it. So the force from the drag then is 44 newtons minus 24 newtons, and that gives you a force from the drag of 20 newtons. All right, so we've discussed forces and Newton's second law in terms of the force being related to the mass of an object and the acceleration of an object. Now, if we change this around a little bit and have mass as the subject of our equation, now mass is equal to force divided by acceleration. Now, we use the term inertial mass to describe this. Now, the inertial mass measures how difficult it is to change the velocity of an object. Now, think about this. If you have a force that produces an acceleration, so you have the resultant force, that force, and we've seen it in some of the calculations, needs to be bigger if the mass is bigger to achieve the same acceleration. So if you have a 20-ton truck and a 900 kilogram car, to get them to accelerate to 60 miles an hour at the same time, you need an awful lot more force to accelerate the truck. And so this kind of resistance to a change of velocity is known as the inertial mass, and we calculate it simply by dividing the force on it by the acceleration that force produces. All right, so here is an example exam question for you. 1. State the meaning of the term inertial mass, and then we have 3 shopping trolleys, different masses, but pushed with an equal force. Using the table, state which trolley has the highest inertial mass. So now these trolleys have different masses, but there's an equal force being pushed on them. Which one has the highest inertial mass? Pause the video and come back. Okay, welcome back. So the meaning of the term inertial mass is the difficulty in changing the velocity of an object. That's what inertial mass is. Now, if we have a look at our 3 shopping trolleys, trolley A has got to a velocity of 1.5 meters per second, trolley B 0.7, and trolley C 2.2. So we're looking for the one with the highest inertial mass. So we're looking for the one that's most resistant to a change in velocity. So it can't be C because that's reached the highest velocity with the same amount of force. So it's going to be the lightest of the 3 trolleys. And so it has to be trolley B that's got to the lowest velocity. That's resisted the change in velocity the most. Right, I'd like you please to summarize the lesson in a tweet, 140 characters or less. Don't worry, you don't have to actually post it on Twitter, but I want you to summarize the lesson in 140 characters or less. What you could do is post that in the comments of the YouTube video down below if you like. Just show the video some love. Boop the like button, and I invite you to stay safe, and I'll see you soon.